Hey everyone, and welcome! So today, we're going to talk about a really cool algorithm. It's all about finding the shortest path, but it's for when things get a little weird. Think of it like a super cautious hero in a world of tricky, deceptive shortcuts. All right, let's get right into it.
Okay, so imagine this. You're using your GPS, right? And it finds this special route, maybe a new tunnel, that somehow puts you a minute ahead of schedule. I mean, it doesn't just take less time, it actually gives you time back. Sounds a bit like science fiction, doesn't it? Well, guess what? In the world of computer science, in network maps and graphs, this idea is totally real.
And that right there brings us to what's called the negative path problem. See, in these abstract maps that computers use, we call them graphs. The connections between different points or edges, they all have a cost or a weight. And you guessed it, sometimes that cost can actually be a negative number.
Now, here's where it gets really interesting. Most of the pathfinding algorithms you might have heard of, like the famous Dijkstra's algorithm, are, well, they're optimists. They assume that every road you take, every step of the journey, is going to add to your total travel time. So a negative edge, a road that saves you time, it completely breaks their brain. Their whole logic just falls apart. They just can't handle it.
So, what do you do when your standard tools just aren't up to the task? Well, you call in a specialist. And for this very specific job, that specialist is the Bellman Ford Algorithm. This thing was literally designed from the ground up to deal with exactly these kinds of weird, complex, and totally counterintuitive situations.
So, what does Bellman Ford do? Well, simply put, it finds the shortest path from a single starting point to all the other points in a network. But, and this is the big but, here's its defining feature, the thing that makes it so important. It works perfectly even when some of those paths have those tricky negative weights.
You could say it has two main superpowers. First, like we've been saying, it handles negative edges like a champ, flawlessly. But its second superpower is maybe even more important. It can detect something called a negative cycle. Now, what's that? It's basically an infinite loop that would make your path shorter every single time you go around it. Think about that. Another algorithm might just get stuck in that loop forever. But Bellman Ford is smart enough to spot the trap and call it out.
Okay, so how on earth does it manage all this? Well, the secret is in its core strategy. It's a really methodical, really patient process called relaxation. The key here is that it doesn't just jump to conclusions. It carefully, and I mean carefully, checks and rechecks all its work.
All right, so here's the game plan, broken down into 4 main steps. First up, we initialize everything. We basically pretend we're totally lost. We set the distance to our starting point to 0, but every other place, we mark it as infinity. We have no idea how to get there yet. Step 2 is the core loop. This is that relaxation phase I mentioned. The algorithm goes through every single connection on the map one by one and checks if it offers a better shortcut. Then step 3, repeat. It doesn't just do this once, oh no. It repeats that entire process over and over again, specifically one less time than the total number of points on the graph. We'll get to why in just a sec. And finally, the all-important safety check. After all that, it does one last pass. If any path still gets shorter on this final check, the algorithm raises a big red flag. It knows it's found one of those dangerous negative cycles.
So why that very specific number, v-1? Well, think about it this way. Let's say you have a map with 5 cities, v equals 5. What's the longest possible trip you can take that visits each city only once? It would have 4 roads, right? v-1. If you add a 5th road, you have to be circling back on yourself. So that v-1 rule is a guarantee. It ensures the algorithm has just enough rounds to find even the longest, most winding path possible without getting trapped in a loop.
And this quote on the screen, this is the heart of relaxation. This is the question the algorithm is constantly asking itself for every single connection on the map. It's basically saying, hey, the path I have to get to V, is it longer than if I first go over to my buddy U and then take the road from U to V? And if the answer is yes, bam, it updates the map. It just found a better shortcut.
Okay, that's enough theory for now. Let's actually see this thing in action. We're going to walk through a simple example, step by step, and trace how the algorithm figures out the shortest paths in a sample graph.
Okay, so here's our starting point. We're at vertex 0. The distance from U to U is, well, it's 0, obviously. But for everywhere else, vertices 1, 2, 3, and 4, the distance is infinity. We just don't know how to get there yet. The map is blank.
And now, the relaxation begins. So, in the very first round, the algorithm looks at the connection from our source, vertex 0, to vertex 1. Let's say that has a weight of -1. Right now, the distance to 1 is infinity.
But 0 plus -1 is, well, it's way better than infinity. So we update it. The new best path to vertex 1 is now -1. The algorithm just keeps doing this for every single edge. And look, after just one full pass, our table is already filling up with the direct paths it's found. And check it out, it's already found paths with negative costs. The path to vertex 3 is now -2.
But here's the thing. The algorithm doesn't stop. It has to be sure. So it starts a second round, rechecking every single edge all over again. It's asking, okay, now that I have this new information, can I find an even better shortcut? Maybe getting to vertex 4 through that new path to vertex 3 is shorter now. Now, in this specific example, it actually found the best paths really early on, but the algorithm doesn't know that. It has to complete all of its required checks to guarantee that the answer is right, and that's exactly what makes it so trustworthy.
And there we have it, the final result. After going through all of its rounds, the algorithm confidently gives us the shortest paths from our starting point, 0, to every other vertex on the map. This is it, the correct, guaranteed to be the shortest set of paths. It handled all those positive and negative weights without breaking a sweat.
This all begs a pretty big question, right? If Bellman Ford is so powerful and so safe, why would anyone ever use anything else, like Dijkstra's? Well, let's get into a final showdown. Because this isn't just about two algorithms. It's about two totally different philosophies.
Honestly, this chart breaks it down perfectly. It's the classic story of the tortoise and the hare. Dijkstra's algorithm? That's the hare. It's greedy, it's optimistic, and it is fast. It just sprints ahead, assuming the path is simple. But if it hits one of those weird negative edge tunnels, it gets totally lost. It just can't handle it. Then you have Bellman Ford. That's our tortoise. It's slower, for sure. It's methodical, it's cautious, and it checks every single step along the way. It's built for that tricky terrain. It handles the negative edges, no problem, and it'll even tell you if it finds a negative cycle. That's the trap that would have the hare running in circles forever.
And that really brings us to the final crucial takeaway here. The choice between these two really comes down to a fundamental question you have to ask yourself. When you're trying to find the best way from point A to point B, is it better to be fast and just hope the path is simple? Or is it better to be absolutely sure, preparing for even the weirdest, most complex routes, just so you know you have the right answer every single time?